Hello, welcome students. I am Tanmoy. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we are going to discuss another methods for pyrrole synthesis, that is Knoor synthesis of pyrrole. Previously I have discussed about the preparation of pyrrole from 1,4-dicarbonyl compound and mucic acid. That means Knoor synthesis, and another is mucic acid and furan. The mucic acid one is a laboratory method, furan is the industrial method to get pyrrole. But this method is mainly useful when you want to prepare substituted pyrrole. Those are very basic and target oriented synthesis, that this material I need, so I have to choose this. But in this way you have a opportunity or option that based on your criteria or expectation you can change the synthons. Okay, so let's start. So as you can see that Knoor synthesis of pyrrole involves, means it's a disconnection approach. If I do, then you can think that in this way this could be disconnected. So what will be the synthon? So the synthon is expected that this is, let's forget about the hydrogen. So we are mainly focusing on the skeleton. This is carbon and this is carbon, plus this is carbon and this is carbon. So we know nitrogen is always delta minus because it's an electronegative atom. So this is delta minus. Consequently, you can expect that the carbon atom, this could be delta minus or plus. Okay. So what is expected? This is delta plus, this is delta plus. Okay. One. And another method, another strategy is that, so we have discussed about the delta plus. So we can change now carbon. Okay. Sorry for this electricity problem. Fine. So this is delta minus. We expect this is delta minus is fixed. So right now, instead of that, we can take C delta plus. Okay. And if we take C delta plus, then actually this carbon and this carbon, this. So it's expected that this carbon means this will be delta minus, this is delta plus. So this is the synthon. Actually, this is the Knoor synthesis, what we are going to discuss today. Why I have given this? And this is actually the Hans method. Hans synthesis of pyrrole. Okay. So we have given, you can, from this you can understand the retrosynthetic disconnection and how to remember. Hans is two positive, Knoor is one positive, one negative. Okay, this is the thing. So today's video, since we focus on Knoor, so we will not discuss about the Hans method. So let's clean it. Now we have understood what is the disconnection approach for pyrrole synthesis. So next question, what is the proper synthon of this? This you can take plus minus. So you can take carbonyl, carbonyl, and alpha to carbonyl is minus. So this. Now question is, what we can take ketone. Means if you can think that this is R1, this is R2, we can take ketone, but actually we will not take ketone. We will, instead of ketone, will prefer to take active methylene compound. Let's take R here, CO2 ET. Let's take, while I'll come. So find this is delta plus, this is delta minus, this carbon. Now what is the proper synthon for this? The proper synthon is, this is delta plus, so you can take carbonyl. This is amine. Okay, so these we can take. Okay, if you want in this position you can take carboxyl, etc. Fine, but this is our main focus. Okay, this. Now question, if this nitrogen, this is delta minus and this is delta plus. So this group, this material, it is active methylene compound 1,3-dicarbonyl. By the way, I'll upload very soon about the preparation or synthetic strategy disconnection approach for 1,3-dicarbonyl. It's a very useful thing. So think, and this is alpha haloketone. This is alpha haloketone. So this is the thing. So this is the basic concept regarding retrosynthesis and proper synthon. Okay. Now discuss about the mechanism. So if you react this, what is chance that if these two are reacted? So first, what will happen? Actually, okay, let's give you the first. So if you think there is a active methylene, there is a carbonyl. One part that they can react, one statement. But keep it in mind, these two protons or the carbanion generated is a relatively soft center because of delocalization or conjugation. But this nitrogen is fairly electron rich, and this reaction, ketone, this carbonyl and nitrogen is a seed-based reaction, is a pretty fast reaction. That's why this reaction will happen more easily. Okay, and generally the medium is basic. I will come. I'm just saying this role of pH. I'll come. Okay, so this attacks here. So what it result? So it's open up R C double bond O. This is NH2 plus, and this is the O minus R CO2 ET. Fine. Now question, it will leave a proton and this charge will be neutralized. So what is the product? This is OH, this is NH. And we know aminal undergo facile dehydration, means it will push, it will leave, ultimately what it will result? It will result this with a plus charge. Second, this proton will be removed, and if it removes, then this is completely a imine with a lone pair. Fine. So this thing we have understood. It's okay. Fine. Now this part till now we have understood. In second step, what is going to? See, we have to prepare 5-member ring and position is 1, 2, 3, 4, 5. So, and second, we know this is active methylene. I told medium is basic. So expected this proton was here will be abstracted by the base and the carbanion will be generated. And this carbanion is resonance stabilized with, first of all, this CO2 ET, second of all, this imine. Fine. I am not going to show this thing. So it will attack in this way. This is a intramolecular reaction. Now question, why intramolecular? We know intramolecular reactions are both. One is highly favorable because of proper conformational orientation, that they can attack. Means simple Bollywood movie example, that when hero used to hit villain, hero hold one hand and hit. That is the intramolecular hitting. And like you can see Chinese movies, they are flying, or Tamil movies, they are flying and attacking. Those are intermolecular thing. I know this is a little funny, but this fun may help you. Okay, fine. Okay, so what happens? It attacks and it opens. So product is R O minus. Fine. This is the N double bond R CO2 ET. Fine. This is the minus, so this is the bond formation. This is this bond. Okay. Fine. Now see what happens. So this carbon till has one hydrogen. If it is not, then material could not be, because this hydrogen should be removed in order to form a double bond, means gaining of aromaticity. So what happened next stage? Next stage, this O minus will be abstracted, will abstract one proton. Fine. And see, if this O minus abstract from proton from some molecule, or for example if you are doing reaction in water or ethanol, what is expected? If it is water, you are taking proton from water, means this abstracted. So what is generated? Is generated O minus, so base is generated. So that base will be useful for abstraction of this proton. Understood? Don't be confused. So if it abstracted, what is generated? The carbonyl is generated. The carbonyl, it is also a carbonyl between two carbonyl group. One is carboxyl. Better to draw in this way, it will be helpful for your understanding. So this is one carbonyl and this is one imine. But actually it's a carbonyl derivative message. So it's a doubly resonance stabilized. Fine. So then it will push, it will go. So what is the product here? Then it will result this is the CO2 EtR, and here one, okay, better to accept this is R prime, then you will have a clear idea. This is R prime and double bond is here. Okay, so you can say this is right now a vinyl gas system. This is alpha beta means imine, alpha beta unsaturated imine, and we know the property shift vinyl gas. What do I mean? You have a imine, this, and alpha hydrogen is acidic. I agree, it is not that much acidic like ketone, carbonyl, but this is slightly acidic, and this is also possible. So what happens? This is abstracted. This is getting abstracted by base, as I told, in because this attacked and this OH minus left. This is another base in the medium. So that base can attack. It will come. Means first base will be generated here. Then this base minus will be delocalized. What is the driving force? So minus in minus here. This is the CO2 EtR. This is the R prime. This. Now see, this is, and when it abstracted another proton from water, if the reaction is carrying out, for alcohol, so what is expected? This NH will be formed. Means the final product is this NH, CO2 EtR, R prime. This. See, the driving force for this step is aromaticity. So please remember this. Why a reaction will happen? This will happen because the driving force is aromaticity. So this is the overall mechanism for Knorr synthesis of pyrrole. Now, during this thing, you have one understanding what is the role of pH. So this part. So see, if you use acidic medium, what is expected may happen? First of all, if you use acid, these NH2 we expect it to remain ammonia, means it is expected to remain as dot HCl. If you use acid, if you take acid, it will remain. And generally, one thing I want to mention that these amines are not stored generally as in amine. It is stored as corresponding hydrochloride salt because it is stable. Otherwise, there is a chance of aerial oxidation, N-oxide formation. Those side reactions are possible. So this. Second, if you keep this NH2, then there is a ketone, there is a chance of self-condensation. What do I mean by self-condensation? Self-condensation means you have a ketone, this, plus another molecule of similar. I suggest you draw the way I am drawing, it will be helpful. So C base means what I told, that you take hydrogen from this H2 hydrogen from amine, and this it will release as water. Similarly this it will release as water. So 2 molecule of water will be released, and what it will result? See, it's a 3 molecule, 3, 6. So at a 6 member ring will form. This, first of all, this is a double bond. See, nitrogen is here. Fine. Similarly, nitrogen is here, double bond, and this is one substitution. This is another substitution. So this is actually the self condensation. Okay. So there is a one chance. So that is the reason why we will use HCl. and in the that is the thing why some modification will come. First of all, starting will be using HCl salt, slow release of amine, because if I explain this thing, you can ask me a question that, sir, in the reaction medium I am doing the work fine, I have taken simple amine because HCl salt will not participate, free amine is needed, so there is a competition between the self condensation, this is you may self condensation, so self condensation versus this condensation, this is self and this is other, so competition is there. Yes, I will, in this condition I can say okay, the major product is this one, fine, but there will be some minor thing. So in order to avoid the chance, or you can say the confusion about small amount of other product, what it's done, this hydrochloric salt is taken and slowly the amine is generated. How you can think this story? For example, same 1:1 they needed, but if you release it very slowly in small amount, so for example in the reaction medium let's have 0.01 mole there and here 1 mole, so 100 times this is, so chances of self condensation minimizes, chances of this maximizes, because surrounding one molecule of free amine there is many molecule of this, so one chance. Second, generate this NH2 from a source pre-amine thing, means some chemical which will be converted during the reaction into amine and it will react. That is one strategy could be possible. Or third, means you can combine this thing. So these two, better to say these two methods. One is HCl salt and there is a precursor for amine you can take in order to avoid this chance of self condensation. So one point we have discussed, and that is the role of pH. And keep it in mind, we can't use acidic condition, because if we use acidic condition, these NH2 will be blocked. So who will do seed base condensation? Possible. But there is another side reaction, that is aldol condensation possible under acid through enol formation. Fine. So that's why we will not use acid. Second, find role of pH. pH is expected to be basic. Now, okay. So this, and second, what I told, that why I have taken active methylene compound, I told that I'll explain. Now question is, I have taken active methylene because this provides selectivity. Why? See, if you take two ketone, this R1, this is R2, so there is a chance that this first reaction will be with this double bond, fine. Now during the second step, means this attack, so from this part attack can happen, from this part attack can happen. Point 1, selectivity. So two types of pyrrole formation possible if we take ketone, first point. Second point, acidity of alpha H, acidity of alpha hydrogen. What do I mean by that? See, when you are abstracting proton from a ketone is not that much acidic compared to active methylene. They are very acidic because the corresponding carbonyl is resonance stabilized by this 2 group. So it is easy to regenerate the carbonyl even under aqueous condition. Okay, that is the reason it is better to this. And you can think, sir, that this is we need this thing. How can we get? See, after reaction, there is a carboxyl group. Fine, do the ester hydrolysis. So if you do the ester hydrolysis in presence of potassium hydroxide as an alkali, this will be carboxylic acid, and you heat it. This potassium salt means carboxylic acid. You heat it. This carboxyl group will eliminate, and which will ultimately end up this. This is R, and this is R prime. So no problem, no confusion. Carboxyl group. So what carboxyl is giving? Giving a selectivity as well as milder condition. So that's why we need this active methylene 1,3 dicarbonyl compound. Okay. So now we will discuss about 3 examples, real examples, to give you the complete understanding. Okay. So let's discuss these 3 problems to understand the topic completely. So first, see, this is actually a real reaction with real conditions. But previously I have explained about the postulates proposals. Now, so this NH2, this 1,3-dicarbonyl compound ultimately results. So at this situation I suggest you, I am going to give you some retrosynthesis of a particular product because this heterocyclic chemistry is an advanced topic. So I believe when you are reading heterocyclic chemistry, then you have learned the basic organic chemistry, organic reaction, so you know, and it is a better thing that you recapitulate your knowledge that how this molecule could be synthesis. Then you can enjoy, your brain will search what will be the method possible. So in this practice will enrich you further about means will make you more efficient to recall the method reactions, because in exam hall or interview time you have to explain by memorizing the thing. Okay, means you have to recall, you have to understand the logic. Okay, so this is this NH2HCl. How it's prepared? This is prepared from alpha haloketone. So what does it mean? For example, you can take this as Br and plus Gabriel Thalamide method. I have already made a video about it. So for that reason potassium thalamide is used, N minus. This. Okay. So this method using. So please be careful. Please try to remember the methods. Fine. How this is prepared? See, it's a 1,3-dicarbonyl compound. So disconnection will be. I will make a video about this disconnection approach very soon. So you can take esters, for example, you can take ethyl acetate plus oxalate, diethyl oxalate. So this anion will be generated attack, and in this way it will result. Fine. Okay. So in under same mechanism I have explained, I am not going to explain again. It will result in this thing. See, this is hydrolyzed very easily because this is more prone because attached to electron deficient part. This, so it is hydrolyzed more easily. First of all, this. If you want further hydrolysis, means this easily decarboxylate, and if you want further hydrolysis in presence of aqueous QH 24 hours, it resulted this. But if you want directly pyrrole, just distill it, because during that distillation process carboxyl will go and pyrrole will be distilled. And one thing, please keep it in mind, pyrrole is a molecule, is highly reactive, is prone for polymerization. So it is better always that before you do any reaction of pyrrole, you better distill, because there may be polypyrrole, because pyrrole is a electron rich. Why? Because 5-member heterocycle and 6 pi electrons are there. So that is the reason for its excessive activity. Okay, fine. So now, as I told that, if first of all you have taken hydrochloride salt, but there is minimum chance also for the self-condensation, that thing could be done a pre-amine thing, and this is the example of pre-amine thing. But you can see this is a nitroso derivative. Okay, so how this nitroso is generated? This nitroso thing, or you can take some other substitute, maybe you can take 1,3-dicarbonyl CO2 like that. Okay, so let's consider this as R. So this, how this could be generated? This is actually a tautomer of nitro. What do I mean? This is R, this is N double bond O. Actually this proton is shifted from here to here and resulted in this nitroso. So how this is prepared? This is prepared from ketone, means this is prepared from the ketone. These and R, better active methylene, I say. This R should be withdrawing like CO2H, this thing. Then this proton is prone, and selectively here ionization will happen, and along with that you can take NaNO2 in acetic acid. So under this condition, what it will do? This NaNO2 in presence of acid will result in HNO2, which looks like this HNO2. In presence of acid, this will be protonated, fine, and it will leave and it will regenerate this NO plus, and this NO plus will react with this. For example, if we take active methylene group, then this, for example, it is CO2 ET. So this under acidic condition, it will not remain in this form, it will be in enol form. So this is the OH. So it will push and it will attack. So in this way it will result this double bond O, CO2 ET and N double bond O. So that is the overall mechanism for the preparation of this nitroso derivative. Okay, so this is a pro, and what happened? These nitroso in presence of sodium dithionate, actually they are reducing agent or zinc acetic acid. Zinc acetic acid, what it does, it produces, actually it's a reducing agent, it gives electron that reduces this, and sodium dithionate is converted to tetrathionate. Okay, so fine, means they act as a reducing agent, so consequently this thing is reduced to corresponding this amine. Fine, so this amine, actually this substitution, so after that you can think this is the R. So then exactly same mechanism which I have discussed, but see, this is generated in situ in the reaction medium, so its concentration is small. Secondly, when we want to do this thing, the general strategy is that this generation, this amine consumption, it is better if it's slowly generated. Then it will react with this and result. So in the reaction medium, there is no chance that concentration of amine is very high, which was the actual problem. That's why we have to substitute from this alpha-amino ketone to this method. So please be smart when you are designing a method. For example, this is one thing, but when you do research, you have to design a molecule, how to design, what strategy, which reaction is good. Keep these factors in mind, it will be helpful to design and choose proper reagent. Okay, fine. So in this way, this could be prepared. So now we will discuss the last. Actually, this example, the last example, is little interesting, because I suggest you, if you forgot the disconnection approach, please go to the disconnection approach again, and there you can see that I have taken plus and minus. What do I say? This active methylene group part, I'll tell you again. This is delta minus, this is delta minus, this is delta plus, this is nitrogen delta minus, this is delta plus. Alpha amino ketone, this. But see, if you think this is also delta plus, this is also delta plus, because that has to. So is it really matching? Actually, this directly does not matching, but indirectly during the reaction you can see that this will not be in delta plus, it will convert in delta minus. So let's see. So see, the medium is slightly basic. Why? Because it's an HCl salt, you have to quench. So the first amine will be generated, and when this amine will generated, means this amine is generated, then it is expected to attack any carbon, because both are delta plus. So fine, if I draw it in a better way, this is CO2 ET. So it will come and it will go. So when it will come again, okay, let me draw it again. It will be helpful for you. So this is carbon COOET attached to this nitrogen. Just I expect that this NH is gone. This is something else. So C double bond COO minus OET. Fine. Now when it will come back, it will this. Generally, you have seen that CO2, this carboxyl group, but then that will be a long double bond chain thing. No. Chances that it can open. Okay. So if it open, what it results? If it open, then actually it results in this double bond formation. Then the charge comes here, minus charge. Now see, previously it was a delta minus, right now polarity is changed during the reaction. That is the smart design. And this reagent is a very useful, this is known as dead diethyl acetylene, because of this part dicarboxylate, 2-carboxylic acid. Fine. So then it will attack here. So if it attacks, then it will be O minus. This is NH. Fine. Now this is double bond is here. This is CO2 ET. This is CO2 ET. Fine. So then it is expected that it will abstract a proton to form this, means this thing. Fine. Now slight amount of H plus is needed. Why? Because see, this results in this elimination of this OH better. Why? It's my personal opinion. See, there are two CO2H, so there is a chance that this double bond, maybe the electron density here is very less between this, because of this withdrawing effect of this two CO2H group. Consequently, so if this nitrogen also wants to push, that may be little difficult. And another thing, electron density may go that side, may go this side. So slight amount of acid protonated this thing, so it leaves resulting a carbocation. So this is methyl, this is N, H, lone pair. So this CO2, and when this plus charge is generated, that is stabilized with this, but simultaneously there is proton. So solvent molecule can abstract this proton and it can prepare this driving force aromaticity. Okay, so in this way this is formed. So these three examples we have read. So what we have learned today, we have learned about the Knorr's method for the synthesis of pyrrole from alpha haloketone and you can better to say active methylene compounds. Please keep this statement in mind. That's enough. Okay, we have learned about the mechanism. Another thing, side mechanism, probability of side reaction, how to prepare synthol, and three different type of ways to prepare this pyrrole in this method. So thank you everyone for listening. If these videos are useful for you, please help me to grow my channel. First of all, please subscribe my channel Chemistry and History of Molecule and press the bell icon to get the notification of every single video I upload. Then there is a chance that you will not miss any video because lots of videos I'm uploading. Second thing, please share this video among your friend. If you share this video among your friend, first of all, it will help my channel to grow. Second thing, your friends will be benefited and they will be the viewer, and if I have more viewer, it encourages me to make good videos for you. Otherwise it's a very disappointing thing and it is very difficult to maintain or upload video on a regular basis if I don't have any viewers. Indirectly it means that these videos are not useful. So if you want, please spread this, and third, may like this video and make some good comment. And if you really think that there is some need of improvement, please mention in the comment box. Your comment, criticism are the inspiration for me for the improvement, and both will be benefited. Thank you everyone. Stay happy, stay blessed. See you in my next video.